Hi everyone, in this video I am going to discuss about page replacement algorithms. But before everything else, let us first recall the topic of demand paging. So in demand paging, what we do is we only load a certain page into the main memory if it is needed or required. So you can see here in the illustration, we have the main memory and then we have the secondary memory. Okay, so initially the processes will be in the secondary memory. And if we need a certain page of a process, then we load it here. Okay, so assuming that the CPU requests the page 2 of process 2. And if it looks at the page table of process 2, it sees that the bit of page 2 is invalid, meaning the page 2 is not in the main memory. So if a certain page is not loaded in the main memory, if it was requested by the CPU, a page fault happens. And if a page fault happens, the OS is requesting from the secondary memory that desired page and loads it in the main memory. Okay, all this page fault is causing a lot of time. Okay, it has to look for that desired page in from the secondary memory, load it in the main memory. So there will be plenty of overhead and additional time spent. Now, another problem is that what if there is no free memory? So here, the OS already found the desired page, but then when it was about to load it in the main memory, it sees that it's already full. So one particular thing that we can do is to do a replacement. So we are going to select a certain frame. So assuming that this frame 6 was selected, so it's called the victim frame. And what we do is we swap it out from the main memory. So now we have an available hole in the main memory, and that desired na page will be loaded in the main memory or swapped in. Now, the problem is how do we actually select the victim frame? How do we perform the replacement algorithm? So there are some replacement algorithms that we can make use of. We have the FIFO or the first in first out, the optimal or the minimum, and then we also have the LRU or the least recently used. So let us look at the first in first out or the FIFO first. So assuming that we have 3 page frames, so what we mean by here is the frames that are available in the main memory. And then we also have 4 virtual pages, A, B, C, and then D. So basically these are pages of a certain process. And then we also have the following stream, A, B, C, A, B, D, A, D, B, C, and then B. So this is the stream of the pages or queuing to use a frame in the main memory. Okay, or pages that are waiting to be loaded in the main memory. So let us start with A. So first in, first out siya. So let's say we load A here. So since A is not yet loaded in the main memory, there will be a page fault. And then B, so we still have free frames 2 and 3. So assuming we put B here, B is also not loaded in the main memory. So a page fault happens. And then C is also not loaded in the main memory. So a page fault happens. A is already loaded. So we do nothing. And then B is already loaded. We do nothing. And then now D is a virtual page that aims to use the main memory, but we don't have any free um, frames yet. So what are we going to do? Which would be the victim frame? And that would be the A, because A was the first one to be loaded in the main memory. So it will also be the first one um, to be loaded out or swapped out. So we replace A with D. Okay, and you can also see it here in the stack. So initially you have A and then AB and then ABC. So we have a tracker here. And then at this time, so we are going to replace um, A with D. Okay, so we have the B and then the C and then the D. So basically what it means is B is now the oldest. So if um, a certain page, for example, that needs to be loaded, then we have to replace B. Since as you can see, and you can also see in the chart here, the most obvious is that B was the oldest. So we remove A. Remove B and then replace it with A. Okay, so you can also see it here. We have left a C, D, and then A. And then next is we have D. So D is already loaded. Then B is not loaded in the main memory since we only have D, A, and then C. And a page fault occurs. And you can see that C is the first one to be loaded out of this three, D, A, and then C. So we replace C with B. And then we use C again. So a page fault happened. So we recently removed the C, right? So currently we have D and A and then B in the main memory. And then the oldest, as you can see, is D. So C will replace D. And now what we have in the main memory is C, and then B, and then A, wherein A is the um, first one to be loaded. And then B. So B is already here. So no more page fault. So how many page faults do we have? We have 7 page faults. So when referencing D, replacing A is a bad choice since we needed A again right away. So what we meant by this one is earlier, if we go back here, we had recently A, B, C, A, B, right? But when D came, it wasn't loaded in the main memory and we don't have available space. And the FIFO mechanism is that the new page will be replacing the first one that was loaded, and that was A. However, it was a bad choice because as you can see, A was used again. So we recently just replaced A. So that means that another page fault occurs. So FIFO is a bad choice. Now, let us look at this another algorithm, the optimal or the minimum replacement algorithm. So we have the same reference na stream. So ABC, ABD, ADB, and then CB. And where will D be brought in? So we are going to look for page that is not referenced farthest in the future. Okay, so still we have we still have 3 frames available. And then we have 4 virtual pages, A, B, C, and then D. And this is the reference stream. So initially A will be loaded. So let's load it in first frame, and then B will be loaded. So then C will be loaded. So since that initially A, B, and then C are not loaded in the main memory, so it is a page fault. Now, A is still already loaded, then B is already loaded. Okay, and then next is that we are going to load D. So in the optimal or in the minimum is that what we are going to do is to look into the future. Okay, so in the reference stream, we can see that the next pages that are queuing after D are A, D, B, and then C. So we are going to look at the farthest away. Okay, so assuming that we look at the 4 frames away, so we can see that we are going to replace D. Okay? So, yung C pa yung last na, matagal pa si C kumbaga ipa-process. So, yung pinakamalapit or nagko-queue ay si D and then si B. So, we will not replace them yet. Okay? So, we replace C with D. And now, A is already loaded in the memory. D is still already loaded in the memory. B is also already loaded in the memory. So can you see the advantage here? So since this A, D, and B were going to be processed in quickly in the future, so we did not replace them yet. And now C, so we have to look for the place where the C will be loaded. Okay, and let's just assume that A is the farthest away, so we replace A with C. And then, yeah. So you can see that there is a minimum of, there are 5 page faults. So if you compare that into the first in, first out, which has 7 page faults. Okay. Now, we also have the least recently used reference page replacement algorithm. So from the word itself, so we are going to look at the um, least recently used na page. Okay, so let's look at how it is done. Okay, so we still have the same reference stream here. Okay, so initially we have A and then B and then C and then A, B. And then the fun part is when we get into this D, wherein we no longer have a free memory. So in the LRU, instead of looking into the future, which happens in the optimal, we look at the past behavior instead. Okay, so assuming that we have here the B, C, A, and then B. Okay, B, C, and then A, and then B. And you can see that the least recently used was C. So the most recently used was B, then followed by A, and then followed by C. Or if 4 frames are past na 4, so you can look at the B also. But still, it will still be C. Okay? So since na C was the least recently used, so we are going to replace C with our new page, which is D. And then next will be A. A is already loaded in the memory. And then next will be D. So D is also already loaded in the main memory. And then B is already loaded in the main memory. And now, next would be C. So currently, in our main memory, we have D, B, and then A. So what we are going to look for is the least recently used. So let's look for B, and then D, and then A. And then the most recently used was B, so nope. Move next would be D, and then the least recently used was A. So we are going to replace A with C. And then of course we indicate that it's a page fault since C was not loaded in the main memory. Okay, and then B is already loaded. So same with optimal, and there were 5 na page faults. So we can see that the LRU and the optimal are so far better than the FIFO. So this is just the stack that we use to monitor our LRU. So as you can see here, A initially was loaded and then followed by A and then B, and then A and then B and then C. So basically this stack are a stack of the least recently used uh, virtual pages. Okay, so say A was the least recently used, then next would be for second. So A and then B, so indicating that A was the least, and then the B was the most recently used, and then the C, B, and then A for the third and the next, and this at this point, so it would be the least recently used. So we just look at this last three. So it will be A and then C and then B, and then at this point it will be B, A, and then C, and then at this point, so the least recently used was B, D here. The most recently used was D. Then next would be B and then A. And then in this, it would be A and then D and then B. So as you can see here, A, D, B. And then in here, D, A, and then D. And then here it is B, D, and then A. And since in C, the C must be loaded and it's not in the main memory, so there's a page fault. And we must replace the least recently used, and it is here. It is the A. So we are going to have C, B, and then D. So lahat ng mga least recently used, so pumapailalim siya kumbaga. Right? And then we add on the top the newer ones. Okay? Now, so when will LRU perform badly? So the LRU performs as follows as the first in, first out here. Suppose we have A, and then B, and then C, and then D. So we have first A, and then B, and then C, and then D. So if we look at the last three, the least recently used was A. So we replace A with D. And then next would be A again. So we are going to look at the last three, and the least recently used was B. So we replace B with A, and then B. So we will replace C. So we look at ADC. So C was the least recently used. Next is C. So C is not loaded in the main memory, and the oldest was D. So we replace C. We replace D by C. And then next would be D. And if we look at the last three, again, A was the least recently used. So we replace it with D, and then followed by A, and so on and so forth. So can you see a pattern here? The stream of the process is of the virtual pages are A, B, C, D, and then A, B, C, D, and then A, B, C, D. So it is done in a circular na manner. So it is done in order. So what happens is using the least recently used algorithm on this kind of sequence of stream of virtual processes, then every reference will become a page fault. Okay, and that's 100% na page fault na rate, and that will cause a 1. So yeah, but if we use the optimal or the minimum, so it performs much better. So let's say we still have the same processor, A, B, C, D, A, B, C, D, A, B, C, D. So first we load A, B, and then C, and then followed by D. So why is it that the D replaced C here? Because if we look at the future, so A, B, C, and then D. So for A, B, C, so the farthest away is C. Okay, so matagal pa siya ilo-load. So we replaced C with D, and then A is already loaded, B is already loaded, and then next C must be loaded, but currently we have D, B, and then A in the main memory. So let's look at the future. So D, A, and then B. So we can see that B is the farthest away. So we replace B with C. And then next, D is still loaded, A is already loaded, and then B. So currently we have A, C, and then D in our main memory, and we must load B, and we must look further away. So further away, so as you can see, recently used are C and then D, but not A. So replace A with B. And if we use FIFO or the LRU, so every reference is a page fault. But in this case, the minimum or the optimal performed so much better. Okay. And next is that adding memory doesn't always help the fault rate. So do you think that if we add more memory, it will also reduce the number of page faults? So it could be for the least recently used and the min or the optimal, but not necessarily for the first in, first out. So it is called as the Belady's anomaly. So let us look at here. So initially we have three page frames, and then we have 5 virtual pages, A, B, C, D, and then E. And as you can see, we have A, B, and then C, and then D. We replace A with D since it's the oldest, and then A, we replace B since out of B, C, and then D. B is the oldest, and then followed by B, and then we must replace C here since out of this three is C was the first one to be loaded, and so on and so forth. Okay, so can we possibly improve this? So if we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, and then 9 page faults. 9 page faults. So can we still possibly improve this by adding more memory? So let us see. So suppose we now have 4 frames instead of 3. So we can see that firstly we load A, B, C, and then D. So in here, we must replace A with a certain page, which is D, but here we have a free memory for D, and then A and then B are already loaded, and then next for the E, so we must look for a new one, and we replace A since it was the first one to come in, and then but we have already replaced A earlier with E, so A must be reloaded and it replaces B, and so on and so forth. So the thing is, we can see that basically the number of page faults are relatively the same, or there is not much improvement. Okay, so we can see that the number of page faults are, well, did not improve even with the addition of a new memory. Okay, so it is not particularly good for FIFO, and again, it's called as Belady's anomaly. Now, how do we allocate the frames? So we mentioned that each process needs minimum number of frames, wherein the maximum number of frames is the total frames in the system. So it may be a equal na allocation or proportional na allocation. And we also have, equal allocation, meaning each process will have equal number of frames, or it may be proportional allocation. So the number of frames that will be allocated to a certain process will be proportional to its needs, or it may be used. It may use priority allocation, wherein we give priorities. We allocate a certain number of frames based on priorities rather than the size. So we also have what we call a global versus the local na allocation. So in the global na replacement, the process selects a replacement frame from the set of all the frames in the main memory. So that means that one process can take a frame from another na process, or one process can take a frame that was allocated from another process. But with a local na replacement, the process will select only from its own set of allocated na frames. So it does not steal other um, frames that were allocated for another process. So it only looks for a frame um, that is allocated for itself. Okay.